Okay, so this is the next lecture in the series on algebraic number theory, and today we're going to be talking about discriminants. So this lecture will be more of a general introduction to discriminants, and the following lecture will be more of specifics of how discriminants are involved in number theory. And these will end up being a really key component both in our proof that rings of integers are finitely generated, but also in how you actually how do you describe rings of integers? How do you find generating sets for rings of integers? So the overview of this topic, at least today's lecture, we're really going to do two things. First thing is just definitional stuff. So we're going to introduce this trace bilinear form. And we're going to introduce the discriminant of this bilinear form. Okay. And the second thing is we're going to prove a proposition which tells you how to use, this is one of the main reasons the discriminant is useful, how to use the discriminant to tell if a collection of elements form a basis. So the idea is this discriminant is going to be some kind of numerical thing that you can compute directly. It basically gives you a computational way to determine if your collection of elements are form a basis or not. Okay. So first let's get into the definitions here. So this is going to be 20.1 definition. So this is going to be a setup for most of this lecture. A contained in B. This is going to be an extension of rings. Where B is a finitely generated free module over A, where B A is a finitely generated free module. Okay, so this the important part is that there's some basis, some finite basis for B over A. So recall we have the trace map. So this is from a few lectures ago. Trace. This is a map which goes from B to A. And essentially what it does is you pretend that an element of B, you can write it as a matrix with entries in A, and taking the trace of this matrix is the trace of that element. Okay. From this we define the this is the trace bilinear form. Okay. So this is going to be a bilinear form, just with the same name, because it's basically the same function. It goes from, so a bilinear form should go from the Cartesian product of your two sets to like the ground ring. I guess, yeah, last time we introduced bilinear forms in terms of fields, but it makes perfectly good sense to talk about it in terms of like A modules, for example. This maps alpha beta to the trace B over A of alpha times beta. Okay, so basically the trace bilinear form says take the product and then take the trace of this guy. Okay, so this is the bilinear form we're going to be using for most of this class. This is why we had the entire lecture on bilinear forms before. And the discriminant is essentially the discriminant of this bilinear form, but in the case of rings, we have to be a bit more careful. Okay. So if, let's say, I have some collection of elements, beta 1 through beta n, then we define the discriminant of these elements by formula. So we're going to use this notation, just capital D of beta 1 through beta n. And this is going to be the determinant. It's essentially going to be what you'd think it'd be based on our previous definition. The discriminant. It's the determinant of the trace. It's determinant of the gram matrix, basically, with respect to these beta sub i's. Now, these beta sub i's don't actually have to form a basis, so it's probably not really proper to call this the gram matrix, but it's the determinant of this matrix. And it turns out that the determinant of this matrix tells you a lot about the properties these beta sub i's hold. Okay. So the first thing I want to say is basically what happens when I if these guys are a basis, what happens when I change basis? What does that do to the determinant? So there's a natural question. Let's say, given a basis, say beta 1 through beta n, for B over A, and let's say a collection of elements, gamma 1 through gamma n, how does, say, d of gamma 1 through gamma n relate to the discriminant of the betas, beta 1 through beta n? Okay. And so the claim is as follows. So proposition, it should be 20.2. Let's say if gamma I, so if we represent basically if we write down the change of basis matrix from the betas to the gammas, and this matrix has entry alpha ij, so if gamma spy equals this, then the claim is that the discriminant of the gammas, gamma sub n, is the determinant of this matrix of alpha i's, the change of basis matrix, squared times the determinant of the beta sub n's. Okay. So the proof isn't actually so bad, so I can explain it briefly here. Proof. I'm not going to go through it in full detail, but I'll tell you basically how you would do it. If, let's say, G is the gram matrix, so yeah, maybe it's not quite correct to say gram matrix, but what I really mean is G equals the trace from B over A of gamma I, gamma J. So the IJ entry is this trace. If G is the gram matrix of the gamma I, and let's see, well, I should not use it again. Let's say B is the gram matrix of the beta I, and let's just say A is this alpha ij matrix, the change of basis matrix. Okay. So if we've got all these, then what happens? Then essentially there's a useful relationship. Then by 19.3, so it doesn't follow directly from 19.3, but applying it a couple times, you can get this. By 19.3 from our lecture on bilinear forms, G is going to be A transpose B times A. Okay, so the gram matrix in the gamma sub i's is related to the gram matrix of the beta sub i's via A in this way. And then basically to compute the determinant, I just need to, or to compute the discriminant, I just need to take determinants. Thus, so the discriminant of the gamma sub i's is the determinant of G, which is, so splitting this and using the fact that the transpose doesn't actually change the determinant, this is the determinant of A squared times the determinant of B, and you can see these are by definition basically the result we want. This is going to be the determinant of alpha ij squared times d of beta 1 through beta n. So this is, I guess there's one thing to see here, which is that this is, this proves, well, okay, maybe I'll make my remarks now. So this finishes the proof here. So 20.3, remark, if these gamma sub i's are also a basis, then this matrix of alpha i's, then the matrix A is invertible. Basically, so just to remind you of why this is true, A is the change of matrix from the beta i's to the gamma i's. We also can make a change of basis matrix if gamma are our basis from the gamma i's to the beta i's, and that will be the inverse of A. Okay. So what do we see out of this? We see that any two discriminants of a basis for B over A differ by the square of a unit. in A. Okay. So this is kind of an important observation here. So this is going to allow us to essentially make the following definition. 20.4 definition. Okay, so we're going to let, A contained in B be as above, so that B is a finitely generated premodule over A. Then, what can we say? I can define the discriminant of this field extension not exactly as an element of A, but up to multiplication by a square of a unit. So then, we define the discriminant. Okay, maybe I shouldn't have changed to red just yet. And we define now I need red. Discriminant of A over B, or B over A, sorry, by, so basically it's going to be the discriminant of any basis by D of A for any basis of beta I up to multiplication by the square of a unit. So this is kind of an annoying thing, right? The discriminant of an extension of rings is not really always well defined. However, in the most common setting, it is well defined. So 20.5 remark. Note that when A equals Z, the discriminant is a well-defined integer. Why is this? Well, this is because the only units in Z are plus or minus 1, and they both square to 1. So both units in Z plus or minus 1 square to 1. So essentially what this definition says in that setting is the discriminant of any basis is well defined up to multiplication by 1, aka it's just a well-defined integer. Okay. So what do we want to end with? So it turns out that discriminants are a useful tool for checking if your collection of elements actually form a basis. Okay, so the following proposition. So we're going to let A. So in this setting, they're going to be assumed to be integral domains. Let A contain in B be integral domains. I cannot imagine a situation in which we would use this machinery when A and B weren't integral domains. I'm sure there probably is one, but and we're going to suppose basically this is not a very restricting assumption, at least for our purposes. we're going to suppose that B is free of rank n, actually rank m, sorry, free of rank m over A. And we're going to suppose that this discriminant of B over A is not 0. Okay, so this is essentially a non-degeneracy condition on our trace bilinear form. Note that if something is non-zero, then multiplying it by the square of a unit is not going to make it 0. So the condition of being non-zero is like a well-defined thing to ask for the discriminant. Okay. And the claim is then a collection gamma 1 through gamma m, is a basis for B over A if and only if the ideal generated by the discriminant is the same as that generated the ideal generated by the discriminant of these guys, gamma 1 through gamma n, is the same as the ideal generated by the discriminant of B over A. Okay, and note again, it doesn't matter which representative in A that I pick for the discriminant, they all give me the same ideal generated here. Okay. That's because the square of a unit is still a unit. So all the possible discriminants differ by a unit, so they all generate the same ideal. Okay, so let's go ahead and prove this proposition here. We're going to let beta 1 through beta m be a basis, and we're going to write gamma I equals sum of the alpha I j beta j. Okay, and we've seen, right, that the discriminant of these guys, gamma 1 through gamma m, is this thing. The determinant of the alpha I j's squared d beta 1 through beta m. Okay. So first let's consider what happens when these guys are a basis. So I guess really the result is clear in that case. It's clear if gamma 1 through gamma m are a basis almost by definition. I guess really this boils down to the remark I was making earlier. Are a basis since then well, I mean, you could even argue that this is like the definition, since then disc B over A equals this thing. I guess really you should think of this as like as a collection of like cosets or something like this. Maybe not cosets, but equivalence classes. And these all generate the same ideal. Yeah, I guess if you really want to be formal, basically multiplication by an element of A cross squared defines an equivalence relation on the set of non-zero elements of A. And I guess even on the set of elements of A, and the discriminant of B over A is the equivalence class associated to a basis, and those all generate the same ideal. Okay, so now what we really want to see is if these two ideals are equal. So if, so now suppose this ideal, okay, yeah, and we haven't used that we're using integral domains yet, so that will come here shortly. Okay, and again, since this is a basis, this is just the same as the ideal generated by the d of these guys. Okay, so if these two things generate the same ideal, what does that mean? Oh, this means that, let's see. So we can find C and A such that C times this discriminant of these guys, K must M, equals, so this thing has to divide, this discriminant of the gamma i's has to divide the discriminant of the beta i's now. Beta sub M. Okay. Now, what does that buy me? Thus, okay, if I multiply both sides by the discriminant or the determinant of alpha ij squared, then I get that C times the determinant of the alpha ij squared times the discriminant of these guys is then multiplying by the determinant of these things and using this guy. This has got to actually equal the discriminant of the gamma i's. Okay. Since this is non-zero, essentially when we want to use integral domain, so I claim this thing is not zero. So note that, well, I know the discriminant of the beta i's is non-zero by a hypothesis. It's not equal to 0 since the discriminant of b over a is not equal to 0. And since these two things generate the same ideal, the discriminant of the gamma i's has to also be not 0. Otherwise, it would generate the ideal, the 0 ideal, and these two ideals wouldn't be the same. Okay, since we're in an integral domain, I can cancel things. Since A is an integral domain, I guess really, maybe it seems like I only need that A is an integral domain. Since A is an integral domain, C times determinant of alpha ij squared equals 1. Okay, and from this, thus, what do we see? We see that the determinant of alpha ij is a unit. So there's, with inverse, okay, with C times the determinant of alpha ij. Okay. Once we know that the determinant is a unit, then we know that this matrix is invertible. Alpha ij is invertible. And once we know this is invertible, then we know that the gamma i's are a basis, because this is the change of basis matrix. If the change of basis matrix is a determinant, or if the change of basis matrix is invertible, then the other, like the image of the basis under this matrix, is also another basis. Yeah, basically, I mean, it's the image of a basis under an invertible matrix is still a basis, and this holds over rings, holds for A modules rather than just over fields. Okay, so what's the, I guess, how do we summarize what just happened, and what's the takeaway here? So the first thing I want to observe basically is, so what just happened, one direction was pretty easy just based on the definition of the discriminant. It's a little confusing, but if you're careful then it makes sense. The other direction is basically if these two things generate the same ideal, then they more or less have to differ by a unit. That's basically what's going on here. And if two things generate the same ideal in an integral domain, then those two elements differ by a unit, and it turns out that this forces the determinant of this matrix to be a unit. Okay, so what's the importance of this? The importance of this is basically that it's almost like an if and only if. Not quite. It's basically saying that if I want to check if I have a basis, so maybe A is Z or something like this, then all I really have to do is compute the discriminant of this thing. And if I already know the discriminant of my extension of rings, then comparing the two will actually tell me what the whether I've got a collection that's a basis or not. I guess in hindsight, this is kind of maybe clear. Like, if I already know what the discriminant of my number field is, then in all likelihood, maybe I already have a basis for this thing. However, I think, actually there are more clever ways we'll see to use this where you don't actually have a basis to start with, but you can use this and some other theorems about what possible values the discriminant can take to find a basis for your number field. So essentially the idea is, like, even though I don't know what a basis is, I can still actually tell you what the discriminant can possibly be. And if I found a collection of elements, basically you can find a collection of elements and then you can narrow down what the discriminant has to possibly be, and you can find that actually the discriminant of this collection of elements has to exactly be the discriminant of my ring of integers over Z, for example, and that'll tell you have a basis. And if this makes no sense, basically, don't worry, because we'll do it in more detail in the future. But yeah, so this is the introduction to determinants, or discriminants, and then we'll talk more about in the setting of number fields and over Z in the next lecture.